All right. Hi, everyone. This is our first lecture for Business Calculus 2. I'm excited to have you in class, and I hope that you find, these aren't really, well, sometimes they'll be long lectures, sometimes they won't. Sometimes I'll just try and, do a little video for you that gives you a bunch of examples, maybe, because I think maybe the book is pretty clear. So, like for this section today, there are some theorems in the book that I think are pretty straightforward. We might write them down and maybe chat about them a bit, but you should be reading the book and then watching this video. So if you haven't read the book yet, you should stop this, go back, read through the book, and then supplement your understanding of that section with one of these videos. But usually I'll try and keep these around 20 minutes. Sometimes if it's a section that I know is a little challenging, then I will maybe make two 20-minute videos, or I'll try and, give you a little bit more than just the book to go on, because I know it's difficult to read mathematics, and it's an art, right? It's something that you have to practice at. So don't get discouraged if you start reading these sections first, and you don't know what they're doing. Contact me if you need help reading through the material. It takes time to get good at reading mathematics. So today what we're going to talk about is anti-differentiation. That's a big word, and it seems like an evil word to me because it's like anti-differentiation, but it's not evil. Nothing in math is evil, right? I know some of you might not agree with that, but basically what we're going to do today is we're just going, as you saw in the book, is we're going to take a function that we know is the derivative, and we're going to see, can I find another function whose derivative is that function that we were given? So before we get too crazy with that, let's recall a couple things, okay? So just in case, I don't know, over winter break you didn't do any calculus, which I feel sad for you. That would be a very, very sad winter break. Let's recall a few rules about calculus. So the first rule that I just want to talk about, well, there's probably one before this, but that's okay. Let's talk about the power rule. Remember what we do? We bring the power down and we take one away. So for example, if I take the derivative of x cubed, that would be 3x squared, as you well know. The one I probably should have done before that, but we'll just put this here, is what is the derivative of a constant? Remember what the derivative is. It's a rate of change. So how does a constant change? Well, it doesn't with respect to x, right? It just goes to 0. Oops, sorry. Let me go ahead and turn off my email so that's not coming up. So the derivative of a constant is 0. Some other things that we found in Calculus 1 that we need to know. I just changed my brush size and I'm not sure why I did that. Remember e to the x, our good friend e to the x? That was a nice one, right? Remember the derivative of e is just e. And then, of course, the derivative of its inverse function, which is the natural log of x. If you have not had Calculus 1 in a while, let me know. I can send you maybe, some of my old exam reviews from Calculus 1. I could give you some suggestions of sections to look at in the book, because I'm gonna expect that you know all of the stuff from Calculus 1. We won't be going over that again. And then another important thing that we need to remember is the chain rule. So if I take the derivative of a composition of functions, right? What is the derivative of that? Remember, we take the derivative of the outside, we leave that inside guy, and then we multiply by the derivative of the inside. All right. So the question that we're going to look at today is, well, let's just write this down, and you probably saw this in the book, but sometimes I can't help myself. If I have some function, if I know big f of x such that, this wording isn't the best, but that's okay. I'm a math teacher. I'm not an English teacher. Such that f prime of x equals 2x plus 1, can we find big f of x? That's what we're asking, right? So if I know that, if I have a function, f of x, and I know that its derivative is 2x plus 1, can I find that original function? So really quick, there was a definition you have in your book, and I'm not going to write it down verbatim, but if big F prime of x equals little f of x, okay, so that would be the 2x plus 1, then the actual function big F of x is called the antiderivative. And again, that just, maybe it's because I like superhero movies. I love like Marvel movies. My husband and I watch those all the time. Antiderivative of little f of x. I don't know why lately I've been thinking about this like a negative thing. It's not a negative thing. It just means we're going the opposite direction. Okay, so we're undoing a derivative. That's what we're going to look at here. So like, let's look at 2x plus 1. You can probably think to yourself, well, I know a function, right, whose derivative is 2x. Namely, I remember that the derivative of 2x is x squared. I also know that the function whose derivative is 1 would just be plain old x. So this is an example, okay, of the antiderivative of, oh, excuse me, that's big F. This is the antiderivative, an antiderivative of 2x plus 1. We're going to see there's more than one. So if you notice, why does that work? Because when I go to take the derivative of x squared, what is the derivative of x squared? It's 2x. Oh, look at that. And what is the derivative of x? Sure enough, it's 1. So these guys match. So x squared plus x is what we call the antiderivative of 2x plus 1. Now, this is an antiderivative. Why is it only one antiderivative? Because, well, look at this, people. Give me a constant. Okay, well, since you can't talk back to me, I'll just pick a random one. How about 14? Look at this. How would I check to see, is this function right here, big F of x, is it an antiderivative of 2x plus 1? Whoa, sorry, I got a little excited with the yellow there. Well, how do we check that? If it is an antiderivative, then I know that that's the derivative of this function I wrote down must be 2x plus 1. Well, if you notice here, sure enough, its derivative is 2x plus 1, because what happens to that 14 when we take its derivative? That 14 goes away. So when we talk about an antiderivative, and I'm not saying the antiderivative, it's because there are actually an infinite number of antiderivatives of a function. Why? Because I know that the derivative of the constant goes to 0 every time. So I can pick any constant I want, and when I take the derivative, that constant disappears. And what do you know? I have that function that I wanted. So there are ways that we get around that. You're like, but Sarah, how can there be so many possible solutions? As a math person, you're like, there's one solution. That's the beauty of math. Well, not always. We're going to get around that by just putting kind of a variable there. And then sometimes if we want to force us to have a constant there, we'll just give some conditions. So yeah, I'm going to stop right there and let's talk about, let's write this down really quick, and then we'll kind of talk about that a little bit more. So again, I'm not going to, I'm not going to write this down completely like in your book, but this is a theorem in your book. You should have this written down. You should copy down the theorems. If you look through my kind of comments on each section under the course content tab under week 1, it'll say section 6.1, and then I'll tell you specific examples to pay attention to. I'll tell you specific theorems and definitions to write down. Sometimes I'll say, write down all the definitions and theorems. They are all important, which I think I did with this section. But then I might point you to some specific examples that'll be most important for us. So this is theorem 1 in this section. Okay, so what this theorem says, if we're going to it says some stuff like let little f of x be continuous over an interval and all of that good stuff. So that basically is just saying that we want these functions to play nice. We don't want to have any breaks in the graph. We don't want to have any jumps in the graph, any holes where we actually can't take derivatives. So let's have f1 and f2 be antiderivatives of little f of x. So again, what does that mean? That means when I take f primed of sub 1 of x, that equals f of x. And when I take f sub 2, the derivative of that, that equals f of x. That's what an antiderivative means. Okay, just get that in your mind. Then, what do I know? I know that these antiderivatives just differ by a constant. Have to. Okay? because I should be able to add any constant I want in there. And notice if I took the derivative of both sides of these equations, right, I would get f1 primed of x equals f2 primed of x, and the constant would go away, which makes sense. We know these two must equal. Excuse me, not the functions themselves, but their derivatives must equal. So when we do examples, okay, something like this, find all antiderivatives. Let's do a simple one really quick, and then I want to show you graphically how this works. We'll do an easy one, little f of x equals 2x, okay? So the way we're going to state this, when we actually state these antiderivatives, I'll use a big F of x. If I want to find all of them, well, what is the antiderivative of 2x? X squared is one of them, because I know the derivative of x squared is 2x. But then what I'm going to do here is I'm going to add this plus c, and that c is usually a capital C, okay? So what that does is that allows us to account for all possible antiderivatives. Any function, anytime I have x squared plus a constant, and I take its derivative, I would get 2x. One thing about this, you always forget that plus c for right now. Start remembering, anytime you take a general antiderivative, start reminding yourself plus c, plus c, plus c. And I just want to show you really quick, if you look at a couple of these, so I could have x squared plus 1, x squared plus 2. These are all examples of antiderivatives. I could just have x squared. I could have x squared minus 1. I could have x squared minus 2. And if you look at the graphs of these, of course you remember from your college algebra course, which we all know and love. If you look at the graphs of these, x squared is just a parabola. Oh, this might be difficult for me to do with my tablet thing here. Here is x squared, okay? If I wanted to graph x squared plus 1, you remember, I would just, oh, they don't overlap, pretend that didn't happen. I would just go up 1. If I wanted to graph x squared plus 2, I would just go up 2. Do you see how, now this does not look very good because I'm not very good at drawing these with this pen that I have. I need more practice. So as the semester goes on, hopefully my handwriting will get a little bit better. But do you see how basically the shape of all these graphs is basically the same? And if we drew any tangent line here, right, that goes maybe through here. If I drew that same tangent line, it would just shift. We'll go right here, up 1. So I would have the same tangent line, right? My derivative would give me the same value for all of these. I would have the same slope for all of these. It's just shifted up and down 1. And then we'll talk and we'll do some examples about how do we pick the actual graph that we want. Do we want the yellow one? Do we want the blue one? Do we want the pink one? Okay, so couple other things about antiderivatives, and this is in your book. You'll want to look at Theorem 2. That's just saying if your function is 0, then its antiderivative is any constant, and we just call that c. The other important theorem that you want to look at is, or definition, is the second definition on page 293. Okay, so definition. And this is just so I don't have to write. So this you're going to need to know. This is our new notation. Okay. This is just so I don't have to write find all antiderivatives of a function. So this is what we call here an integral sign. So this is called the integral. This right here is what we call the integrand. Okay, that is the function that we're trying to find the antiderivative of. Again, this is just notation. This is just like when we use the d over dx to indicate we're taking the derivative. Here what I'm doing is we're bringing in a new notation, and we'll talk about why it's this like elongated S looking thing later. But for right now, what this integral sign means is just find all antiderivatives of the integrand, or of f of x. And then this guy right here, again, we'll talk about this a bit later, but this is the variable of integration. So a new term then for finding antiderivatives, we also could have called this integration. And if you look at chapter 6, the title of chapter 6 is called the definite integral. So we're going to talk about what that integral means. So what I'm asking us to do is when we have the integral of f of x dx, we're integrating f of x. What does integrating mean? It means find all antiderivatives, okay? And so before we start getting too crazy here, what I would like, and this is also, can I just say that this is called, well, I'm going to say it because you guys can't stop me because you're not here. This is called the indefinite. I have way too much fun doing these videos all by myself. This is called the indefinite integral. Eventually we will talk about something called the definite integral. Oh, it's just going to be so much fun. You guys are going to just love it. This class is so fun. Okay, so some useful rules about integration, which again, I could say anti-differentiation or integration. It doesn't matter right now. So some useful rules for us that we should know. We should know these rules because basically, let's go back to this. Oh, there. Let's go back to this layer, this, sheet right here. Basically, what we're going to do is we're going to be going the opposite direction. So instead of taking a derivative, we're going to start with something like this, and we're going to go backwards. But we're really going to put it in that form. But let me just, let's do this. So I'm going to write down these rules and then we'll talk about why, why do these rules kind of make sense, okay? So the integral of x to the r with respect to x. So this is saying I want to take the antiderivative of maybe x cubed. Well, what did the derivative do? We brought this down and multiplied by r and took one away. So now what we're going to do is we're going to do the opposite. We are going to, instead of taking one away, we are going to add one to the exponent, and then we're going to divide by the resulting number, right? That would make sense. Again, I'm taking the antiderivative. Why would this work, right? Well, let's look at this, people. Let's take the derivative of x to the r plus 1 all over r plus 1. What do I know I do? I bring the r plus 1 down, right? So I'm going to have r plus 1, okay, times x to the r plus 1, and I take 1 away. And then this r plus 1 on the bottom would just hang out because it's just a constant. So look at what would happen. The r plus 1s would go away. These ones would cancel. And what do you know? The math gods are smiling on us because we just get x to the r. Other thing here that we need to make sure, though, r cannot equal -1. Why can it not equal -1? Because I would get a 0 in the denominator. And these are all in your book. These rules are, in like page 295, page 294. This is all in your book. So I'm getting a little, sorry, I get a little excited about some of this, and you've already seen some of this. So let's just write these down really quick, and then I want to do some examples. This guy right here, the antiderivative of e to the kx, where k is a constant, is 1 over k, e to the kx. Where does that 1 over k come from? Because remember, when you take the derivative of e to the kx, you must use the chain rule, so that k is taking care of that. The integral of 1 over x, which is x to the -1, right? What function has the antiderivative 1 over x? This is the natural log. Now, this is going to be the tricky part. When you take the antiderivative, you must use absolute values. Remember, the domain of natural log are positive x values. Over here, this 1 over x has not said that x must be positive. You can take 1 over negative numbers. But when we go and bring in a natural log that wasn't there before, we must put absolute values because we can only take the natural log of positive numbers. Okay. There's the addition. I can take, you can look at that one. That's on page 295, the basic properties of integrals. I'll let you look at that. We can distribute integrals over addition, and if we have a constant, we can pull the constant out. Okay, let me tell you what we cannot do. We cannot distribute integration over multiplication and division because we know we need the product rule and the quotient rule. Oh, I'm almost at 20 minutes. This one's going to go a little bit longer than normal. Sorry about that, but we'll be all right. So let's do a couple examples. Okay, so example, let's take the integral of, oh, I don't know, how about, let's just start off kind of simple. X cubed minus x plus 5, okay, dx. So if I look back, what is my power? That first rule we wrote down was something called the power rule. So what that says to do is add 1 to the exponent, so 3 plus 1 is 4, and then divide by that. Minus, this is x to the 1, so I would add 1 to the exponent, x squared, and divide by 2. This is 5. What's the antiderivative of 5? Remember, that's basically 5x to the 0 power. So I'm going to add 1 to the exponent, which would be 1, and then divide by 1, okay? And I just get 5x. The great thing about integration is that you can always check yourself by taking the derivative. Now let me show you the way that I will probably write this. I will probably write this as 1/4 x to the 4. I don't know why I don't like it like this. It's not wrong. I just like having that coefficient. You would agree with me, right, that x to the 4th over 4 is the same as 1/4 x to the 4th. Then I would subtract, I would just do 1/2 x squared plus 5x plus c and call it good. Okay. Again, if you took the derivative of this, bring the 4 down into front. 4 times 1/4 is 1, and take 1 away. Bring the 2 down, they would cancel. Take 1 away. What's the derivative of 5x? That's just 5. And what is the derivative of any constant? It's 0. So sure enough, I have found the antiderivative of x cubed minus x plus 5. Good. Let's look, I want to look at another one. How about something like this? What if I had 1 over the square root of x minus e to the 3x dx, okay? So first thing I'm going to do, which remember, even if we were taking the derivative of this, we would have done this in Calculus 1. I am going to rewrite this a bit, okay? This would be x to the negative 1/2 minus e to the 3x, okay, dx. So what is my I'm going to come over here and give myself some room. My antiderivative then would be x to the negative 1/2 plus 1 all over whatever that number is, which I really hope you can take a negative 1/2 and add 1 to it in your head, minus, now remember what, I erased it. So remember, what is the derivative of e to the 3x? Well, I know it's going to involve, whoops, an e to the 3x, right? But remember, if I just put e to the 3x here, that would be wrong, because when I take the derivative of e to the 3x, I have to do the chain rule. The chain rule says take the derivative of e to the 3x, just rewrite it, and then multiply by the derivative of 3x, which is 3. So notice, if I just leave e to the 3x, that's not the derivative. That's not right. We're off by a factor of 3. So I need to bring in a 1/3, because then when I bring in that 1/3, do you see how those guys will cancel? And sure enough, I'll be left with what I started. And then finally, I need a little bit of plus c here, because we want all the possible antiderivatives. Okay, so let's simplify. Let's clean this up right here. Negative 1/2 plus 1, if you take half from a whole, you're left with a half. So this equals 1/2. And what do you do when you divide by a fraction? You flip it and multiply. So that would be 2x to the 1/2 plus, no, minus, excuse me, 1/3 e to the 3x plus c. And then remember, take the derivative, check yourself. You might as well, especially when you're on a test or something, check yourself by taking the derivative. And a sufficient answer here too would be 2 square root of x minus 1/3 e to the 3x plus c. All right, let's do about 2 more examples. I think I'm probably losing you because it's 23 minutes in, if you haven't fast forwarded already or given up and you don't even hear me. So let's look at one more example. What if we had the integral of, I just want to do something kind of interesting here. Not that these all haven't been interesting. Yeah, let's get a little crazy. So what if I had 3x to the 4th minus 2x squared plus x minus 1 all over, how about, let's do x cubed. Okay, this one's going to be a little tricky, dx. Now, the reason I wanted to show you something like this is here's what you cannot do. You may not take the integral of the top over the integral of the bottom. We have nothing that says we can do that. We know we use the quotient rule when we take the derivative of a quotient, so wouldn't it make sense when we take antiderivatives to not use something like the quotient rule? We don't know what that is yet. So what I need to do is I need to do some algebra, right? Which we're excited about because we all love algebra. I had a mentor in graduate school who used to say it's not the calculus that's hard, it's the algebra, which I think can be true sometimes. Remembering all of these algebra tricks can be tricky. So look at what I'm doing here. I'm dividing each term by x cubed. And now this is what we would do anyway if we were taking the derivative of this. If we were taking the derivative, not the antiderivative, I wouldn't be using the quotient rule. I would be simplifying this using my mad algebra skills with a Z. I don't actually know how kids talk these days, but I pretend. My students assure me that I actually don't know. All right, and so now I have 1 over x squared minus 1 over x cubed, and I'm even going to go farther. Again, I don't care, I'm not an English teacher. And I'm going to rewrite this a little bit more. Now, I'm going to put 3x is just going to hang out. I'm going to bring this 2 out front. I'm going to write that as 2 times 1 over x because I recognize 1 over x is going to bring me a natural log. Then here, I want to use the power rule. Just like if I were taking the derivative, I would rewrite this. When I take the antiderivative, I'm going to rewrite this as well. Okay, I don't need these parentheses, but I like to put them because it helps me see what's going on. Let me, I'm not quite used to writing on this still, so I'm going to erase this stuff. I hope you got it, so that I can have a little bit more room, but I can still see kind of what I'm doing. All right, thanks for bearing with me. You don't really have a choice, so. Okay. Okay, so now I'm ready to rock and roll. So let's go ahead and take the antiderivative. So again, I have 3 times x squared over 2. Remember that 3 can just hang out because it can hang out when we take derivatives as well. Here, what's the derivative of 1 over x? I'm getting ahead of myself. It's the natural log of the absolute value of x. Derivative of x to the negative 2. So don't let silly arithmetic get you down. This is negative 2 plus 1. Okay, so think about that. What is negative 2 plus 1? That is negative 1, and then you must divide by it. Minus, I'm going to clean this up. This if it's bothering you, it's bothering me too. Don't worry. Add 1 to negative 3. I get negative 2 and divide by it. And then don't forget your plus c. And now let's make this look a little prettier. So what's my final answer? 3/2 x squared minus 2 natural log absolute value of x. This negative 1 can just become a negative. Now that you can leave this as x to the negative 1, or you can write that as 1 over x. I don't really care, either one. Here my negatives will cancel and become a positive. And I would probably write this as 1 over 2x squared. But again, you could write that as 1/2 x to the negative 2, and that would be fine as well. All plus c. That is my antiderivative. Pretty cool, huh? 20 minutes. Let's do one more example, and then I promise I'm going to stop talking. I know, I tell my husband that a lot too. But, so find f of x such that, okay, here's what I know about f of x. F primed of x is 100 over t squared, and f of 1 equals 400. So this is what we call a differential equation. We've dealt with this before. It's just an equation involving a derivative. So what I want you to find is I want you to find f of x such that its derivative is 100 over t squared. So I definitely need to find its antiderivative. But I've also given you some more information. Not only do I want its derivative to be 100 over t squared, but I want, when I put 1 into the function, I want it to spit out 400. So let's start off by finding little f of x. And little f of x here is going to be the antiderivative of 100 over t squared, which I'm going to write as 100t to the negative 2. And now I have dt because I'm not dealing, oh, why do I, you're like, Sarah, why do you have x's when I really am in t's here? Excuse me, my goodness. first lesson. I'm sure I've already made several mistakes and you're yelling at the computer screen. If I make mistakes in these videos, would you please send me an email or just, send me a quick note and be like, Sarah, you made a mistake, which happens often because I just get so excited and I start talking. It happens to the best of us. So let's see what we get here. I'm going to get 100 times t to the negative 1 all over negative 1 plus c, right? These are all possible antiderivatives of f of t, not x, okay? So let's clean this up a little bit. So I know f of t then is going to equal a negative 100, and I might as well put that t on the bottom, over t plus c. So these are all possible antiderivatives. These are all the graphs, right, that satisfy its derivative being 100 over t squared. But what I want to find, this right here tells me I want the graph that goes through when t is equal to 1, f of 1 is equal to 400. I want the graph that goes through the point 1, 400. So how do I find that? Well, what does f of 1 mean? That means wherever I see a t, I'm going to put a 1. Isn't that convenient? And I want what do I want? I want when t is 1, I want this whole sucker right here to equal 400. Isn't this great? I love doing these. So now look at what I have. I have an equation that lets me find this specific c. And so what I find is that c is equal to 500. Now this is not my answer. My final answer should be a function, right? Find a function. So what is, and I know you're going to get annoyed with me being so anal about stuff like that, but I'm right about it. Your answer should be explicit. You should tell me, Sarah, my answer is negative 100 over t plus 500. That is the function, right? So this 500 right here goes in for this c. This is the function that satisfies these two conditions I was given. Okay, so that was a long lecture. There is one more example that I wanted to do, but I don't really have time, I don't think. But what I would like you to do is make sure that you read over and copy into your notes example 8. It's pretty self-explanatory, I think. On page 296. This will help you in how to do some of the applied problems. Remembering that when we talk about marginal cost, remember what marginal cost was? Marginal cost was the derivative of cost, and what it did is it gave us the, whatever number of units we want to sell, it estimated the amount it would cost to increase production of a unit by however many, by 1 or whatever we have. By 1 at that production level. So please look over that. Also, I have something in this class called fun sheets. So when I have my face-to-face class, we work on them in a group, but because we don't have that here, the fun sheets really, I don't like calling them worksheets because it's not work, it's fun. These are available on Blackboard. If you look at the tab on the left, it'll just say fun sheets. It's extra practice for you. So the way you get good at mathematics is you actually need to do mathematics. So you need to be looking at the suggested problems that I give you. Look at the assignment for 6.1. Those are all odd. All of those answers are in the back of the book. Then you'll be turning in the required problems. You do not turn in the suggested. You just turn in the required problems. You can take a picture of it with your phone and submit it, or you can scan it as a PDF file. I'll take either one as long as I can see it, as long as the picture's clear. I'm happy with a picture from your phone. And then work on the fun sheet also. So the fun sheets will be up. There will be a blank copy up, and I'll post the solutions as well, so you can see how I'm doing these problems, kind of look at how I do those problems, and then work on your own. Also, anytime you need help, you can always contact me. Send me an email, call my office number and leave a voicemail, and I'll get back to you. I say within 48 hours. I usually try and get back to you sooner than that, but just with everything else going on, it might take me, a couple days before I get back to you. As always, please don't hesitate to contact me, and I look forward to our semester together. Thanks.